So two principles we're going to need. I'm going to get to the first one later, but I've said basically a wire placed in a changing magnetic field can serve as a generator. I generate a voltage inside of a wire if I place that wire inside of a magnetic field that's changing. Okay. All right. So, and these are posted on the website if you want to work from those. All right. So basically, in any of these problems, we got to make electrical circuit models. So we're going to deal with electromagnetic devices. Right now, we're focused on transformers. A motor is a similar thing. If I look at a motor, you might have seen these before. If I look at a cross section of those, there's a bunch of coils on it. All right, we'll look at those later. Basically, our idea is I want to figure out a circuit model for this thing. So this is a motor. It's going to have three phases. It's going to have three circuits on it. So what I do is I build a magnetic circuit model, and then I convert that magnetic circuit model to an electrical circuit model, because that's ultimately what we hook up to, the electrical circuit. So for the transformer, right, what we said is I've got two coils that are coupled together. I'm going to send an announcement about this, but we're actually going to go into the lab on Wednesday next week. So I determined that's the day we're going to do it. We're going to go in there, we're going to make some measurements together and try to look at a transformer, a real transformer, rated for about 1 kVA. All right, that's something on that scale. Ideally, what I would have is that the flux linking both the coils would be the same. All right, I want the flux from one coil to cut through the other coil. To make that happen, what do I need to do?
What do you mean cut?
Well, I want to make sure that if I put a current source over here, right, and I left this guy open circuited, the other side open circuited, that's going to create a flux in coil 1. I want to make sure that all of the flux created by coil 1 cuts through the center of coil 2. I don't want any of it to do this, because it could do that. It's possible that some of the flux could escape the core. Now, magnetic flux lines always have to be closed, right? You guys learned that in fields, right? So that coil is going to make flux that goes in the direction that I'm showing here. But what makes it such that it all goes not coming out into that circle? What makes it go around through the core? What makes that happen? What makes it stay in the core? Not I2. We'll look at this when we're in the lab next week to make sure you really believe it. What? No. No. I need a core. I need iron core that's really good, really highly permeable. I need to make sure if I have an infinitely permeable piece of iron, then all of that flux will be directed from where I created it here in coil 1 to where I want it to go in coil 2.
So the path of least resistance is through the coil.
Yes, the path of least resistance is through the coil. That's exactly the way to say it. The path of least reluctance for the flux would be through the other coil. All right. The path of least reluctance in this case. But yeah, you can think of it the same way. Ideally, the mu of it would be infinite. If the mu is infinite, I guess I have it written here, length of the core over mu area of the core. This is 0, right? And so anytime we talk about the length of the core, right, it's always an approximation. This is something that probably messed a lot of you guys up. It's the middle of that thing around that path. All right, that's what we consider to be the length of the core. Right, we could do the calculus and calculate the volume and stuff like that, but everybody just uses that middle value. Okay. All right. So I got 2 steps to that process. I make the magnetic circuit that leads to an electrical circuit. How do I make the magnetic circuit for this guy? We've done it a couple of times now. What's in the magnetic circuit? Yep. And so how many MMFs do I have? 2. And I've said this before now, but I put them both in the same direction. Why is that? For the direction of currents that I've drawn here, both of them are going to push flux in the same direction. Okay. So I'm going to have this. That's phi. Yeah, because with the currents going in, if you do the right-hand rule, both of them are going to make flux that go in the same direction. If one of the currents was going out, then it would be forcing flux going the other direction. and I would draw the MMF the other way. Okay. But based on the way I defined it, this is the way it would be. And it's no big deal. Let's say the current actually was going out. Well, that would just end up, if the current was negative, this guy would just end up flipping itself around. All right. The math, it's one of those things like in circuits. If you choose the wrong direction, it's not a problem. You're just going to get a negative answer. Okay. All right. So we got that. If I wanted to know the flux, what is the flux here? In terms of all the crap that I have written in that picture. So N1I1 plus N2I2, right? It's just simply a statement of KVL here. So N1I1 plus N2I2 over the reluctance of the core is flux. Now, what I do is I turn that into flux linkage, and I figure out what's lambda 1 and what's lambda 2. So how do I figure those out? Lambda 1 and lambda 2. What's that?
The formula.
There's a formula. Fuck the formula. Oh, I should have recorded that. Sorry, it's been a long day. Okay. I should. Oh, well, you guys, you guys have insights into my mind. All right, so let's see. So, but let's not think about the formula, right? So, what is flux linkage and what is flux? Flux is the magnetic field that's going through. What is flux linkage? Yeah. So basically, what you're saying is flux phi is going through each one of those coils. And so if I put a bunch of coils in series with each other, what I'm saying is the entire coil has n times that going through it, right? Now that's important to me because this is the linkage to the voltage, right? If that magnetic field is changing, what do I know is, so because again, my two steps were what? My two steps were build the magnetic circuit model, and then use the magnetic circuit model to derive the electrical circuit model from Faraday's law. Okay. So I'm at the end of step one. Basically, what I've done is I've figured out the flux. Faraday's law is the linkage now to a circuit model, right? What's Faraday's law? Creates a voltage. Yeah. Let's say it's simpler. You guys know it from a, d by d, whatever, through an integral and all that. You guys know it that way. But if I just think of it in terms of, if I have a changing magnetic field through a coil, there's a voltage that's created. So V equals d lambda by dt. The voltage is the rate of change of flux, is what that says. That is the same thing ultimately as what? L di dt. Right? You guys know L di dt. Basically, that also is Faraday's law. All right, so what does that mean? That means I basically take the derivative of these two results. That's going to be the voltage on those coils. So if I do that, right, I have basically, here's lambda 1, here's lambda 2. Looking at those two expressions right there, right, if I take the derivatives of those two things, I'm going to get V1 is d lambda 1 by dt. So just real quick, if I take the derivative of these two terms, this term and this term, what about this? What about these terms out in front? Do those change with respect to time? They do not, right? They don't change with respect to time. In fact, they have the general form of inductances. And so I call this guy right here, I call it LM1. And I call this M. Mutual inductance, okay? And then similarly over here, this guy would be V2 equal to LM2 di2 by dt plus M times di1 by dt, okay? So if I look at those two things, I can make a circuit model from it, right? And that is what we sort of did the other day. So I made a circuit model for, let's say for this guy, which had in it, the way that I drew it was I said, so I did this actually with phasors, right? So if I do this by phasors, I would say the V2 phasor. What do I do with d by dt's when I do phasors? What's the derivative become if I do phasors? Yeah, and so I'll say J omega. It could be S, yeah. J omega LM2. You're good, yeah. S. I like S better anyway, probably. Right? So what I did was I said for each of these two sides, one way of thinking of this thing is to say, here's V2. I2 I'm showing going in. Why did I show going in? Because it was going in here. So I'm making it going in here too. All right. What I'm saying is if I did this circuit, here's LM2, and here is a J omega M I1. If you did KVL around this circuit, you would get that result. In other words, I just drew a circuit model that's entirely consistent with what I got from doing magnetic circuit and Faraday's. Right. So in other words, I've got an equivalent circuit model that describes if I hooked a voltage source up here, what would happen. Right. That's our basic analytical approach. Okay. So I derived everything like this. This is one way to think of things. And this is how we're going to look at things like synchronous motors and generators and induction motors and stuff like that. Transformers, we usually think about a little bit differently, right? We can think of them this way, but oftentimes we think of them in terms of the ideal, the real, and what I say is the real with leakage. Okay, so when it's ideal, what's true about it? Well, we've talked about this. Basically, what makes the transformer ideal? The mu, yeah. So basically, what's the mu have to be? Infinite. What's the reluctance then? 0. So in that particular case, these two things become true. And I use this circuit model. The inductances here basically become ultimately infinite in that particular case, right? And so these models get a little bit tricky to use, right? So are these inductors in here? They are not inductors. This is a circuit symbol. It's two inductors facing each other, right? They're not actual inductors. That's just what we show. And what I use is the dot convention. The dot convention basically says, if I have a current that flows into the dot on one side, that current will flow out of the dot on the other side. All right. And all the problems we have, that's going to be the case. All right. So let's look at now the non-ideal transformer. All right. So I do it two ways. The first one is, let's assume that the mu is pretty darn big, but not infinite. Okay. Now, in theory, what should start happening then? If the mu is not infinite, then there should be some flux that's leaking out of this thing. But as a first pass, I can say, let's assume that flux is really, really tiny. Now, we're going to come back to it. We're going to say, let's assume it's not that tiny. Well, let's start here, because we oftentimes we do start here and say, well, let's just say mu is really big, but not infinite. Does that change the circuit model? Doesn't change it, except for the fact that I have this statement here. If I was in the case of the ideal transformer, right? What would be happening in the case of the ideal transformer? Yeah, well, so in the case of the ideal transformer, the reluctance would be 0, right? So these two would have to balance each other, or else, the gates of hell would open, right? I would have no resistance in that circuit, and there would have to be a ton of current flowing, right? So what has to be true if it's an ideal transformer is these two exactly balance each other. In a real transformer, they don't have to balance each other. The difference between them can just sit across the reluctance, right, and lead to a flux. So if I go through the analysis here, basically we've already done the analysis. This is what we have. Here's lambda 1, here's lambda 2. I solved for the flux. We did that already for this same circuit. Nothing's different. Okay. However, when I look at this, okay, when I look at this, what I see is I want to take this again to a voltage. All right. My magnetic circuit analysis got me to these flux linkages. So to see how long you can retain this, okay, how do I relate this to a voltage? Now that I have a flux linkage, how do I relate that to a voltage? What's the relationship to get that to a volt? Yeah, which is what? I just want to see if you remember it from when we last talked about it a couple minutes ago. As long as he's got the sense to go back, I'm good with it. Right. Well, all right, so if I have a lambda is a flux linkage. How do I get, so what's supposed to a flux linkage supposed to do? If I have a flux linking a coil, it creates a what? It creates what? Creates a voltage, right? And so we have the V equals what? D lambda by dt. Yeah, right? V is d lambda by dt. Okay, so again, we already said this, but basically what that means is if I look at these two coils, I'm going to focus on just coil one for the moment. Okay, here's coil one. I take the derivative of this expression. But because I don't like derivatives. I like to deal with phasors, right? They're a lot more fun than differential equations. So I'm going to turn it to phasor form. So instead of taking the derivative, what do we do if we're in phasor form? Multiply by S, or j omega, right? So V1, the phasor, would be j omega lambda 1, which would be, for what I have right here, it would be j omega times N1 squared over the reluctance times I1 plus j omega N1 N2 over the reluctance times I2. You guys with me on that? Okay. Now I'm going to make a definition. I've already said this. N1 squared over the reluctance. What did I call that? I gave that a name. Well, first of all, what is it?
Your signal function.
Yep. What is, so we defined what, we gave that a name. Anytime I have an N squared over a reluctance, that's a what? Let's look at it here. It's first of all, anytime I have an N squared over a reluctance, it's an inductance. Okay. And I call it the magnetizing inductance. Okay. So in this case, what I'm going to say is this first term is j omega. I could call it L mag 1. I'm just going to call it L mag right now. LM, I'm going to call it L mag. Okay. Now, what was N1, N2 over the reluctance? It was M, the mutual inductance. All right, I'm gonna take a look here though. Let's say I did this. So M is N1, N2 over the reluctance. Let's say I did N2, just a math trick here, N2, N1 times that expression. Right? Those guys are equal to each other, aren't they? If I multiplied that thing by N1 over N2 like that, those two are equal to each other, aren't they? All right, so I'm gonna use that fact. And what's that? No, because what's gonna happen if I multiply these two together, N2 and N2 are gonna cancel. I'm gonna have N1 squared. Well, I guess I gotta be careful. If I look at this, yeah. If I multiply by N1 over N2, I guess those are not going to be equal to each other, right? This would be equal to LM like that, right? There's a reason why I'm doing this, right? Basically, what I can do is I could rewrite this second term over here, and I could say that it's j omega times N2 over N1 times M times I2. In other words, I took this expression right here, and I said it was equal to this right there. Okay, which is what I've done right there. All right. Now, why did I do that? All right. So this guy basically is j omega L mag I1 plus j omega LMAG. Sorry. Yeah. Sorry, this was M. This is N2 over N1 times LMAG, like that. Okay. All right. What I did was I basically said, if I take M and multiply it by this expression, it becomes LMAG. So I use that here to rearrange everything. Now, why did I do that? Well, let's look at this circuit model right here. Okay. Yeah, let's look at this circuit here. Right? Just pretend that this circuit, we didn't see anything that we just did because you guys don't remember it anyway. But we're going to go back to it in a second. I don't expect you to remember. You shouldn't remember it. If I said to you, okay, let's do circuit analysis right here. All right. So in other words, I want to figure out what's the voltage going across this thing. So V1, let's say I put a voltage source there. Tell me how I could figure out the current in this particular loop. That IMAG that I wrote here, so which is actually what you need in your homework. I called this current IMAG. Okay. In terms of just a KVL, or sorry, KCL, what is IMAG in this circuit model? Forget the term. Just say I just drew an arrow there and I called it IMAG. What's that current equal to? Do it in terms of KCL. So I got three currents there, right? IMAG's coming out. Yep, N2 over N1 times I2. Okay, now, where did I get this? This kind of showed up arbitrarily. What is this thing? This is an ideal transformer right here, right? This is an ideal transformer. What I'm saying is if I know this current, then I can figure out that current through the turns ratio. Okay, that's what I did. So I know this current through the turns ratio. All right, so that's this combination of stuff I call IMAG right there. So that means that V1 has to be J omega LMAG times IMAG, right? How did I get that? I just did KVL around this loop right here, didn't I? So if I plug in J omega LMAG, I'm going to plug in this expression here. And I'm going to say I1 plus N2 over N1 times I2. Okay. That's the same thing I wrote right here. So what I have is basically, what I'm saying is this circuit model is entirely consistent with what I got when I derived everything from the magnetic circuit model. And so this is what we term to be the model of a real transformer, quote unquote, without leakage. All right, it has a magnetizing inductance. What does that magnetizing inductance represent? Let's think about it. I think of it like this. As I go from an ideal transformer to a non-ideal transformer to a more non-ideal transformer. Okay, so when it's ideal, I have this relationship between the voltages and the currents. How much flux is supposed to be in the core if it's ideal? So what was the reluctance of the core if it's ideal? 0. So there should be 0 flux in the core. All right, weird thought, but there should be 0 flux in the core. Basically, the two MMFs balance each other. If I have a real transformer, I said, well, the mu is big, but not infinite. So that means that there is some flux in the core. We call this guy the magnetizing inductance because it represents basically the impact of magnetizing the core. The fact that there is now a magnetic field moving through the core. When it's ideal, there really isn't, right? Which is a weird thought, but when it's ideal, it doesn't need that. Okay. So we have that model. Now that's not the complete model. Actually, the more complete model is if I include what I call leakage. Okay. So what I did here is I drew 3 flux paths. All right. There's a flux that goes from coil 1 to coil 2. We already talked about that. What I have in here is what I wrote as phi L1 and phi L2. That represents what? Yeah, leakage. But why did it? So why is there flux that's leaking out of the core and not making it all the way around? We said why already. Yeah, the fact that the permeability is not infinite, right? So some of the flux, hopefully a really small amount, maybe only a couple of percent, maybe not even a couple of percent, maybe only 1% of the flux leaks. But it does leak and it doesn't go through basically the key thing is that it does not go through the other coil. It doesn't have to be coming out where I showed it. It's not going to have a nice, neat path like I showed it. But the important thing is that some of the flux created by coil 1 doesn't go through coil 2 and vice versa. All right, so if I drew the circuit model for this, what the heck would it look like? Well, it's complicated, but it would look like this, N1, I1. It's not that complicated. N1, I1, and N2, I2 are still in the same direction, right? I still have the reluctance of the core. Yeah, and there's additional reluctance for each leakage path. Where would those go in this circuit? How about I say one of them is, let's say RL1. Wouldn't it be in parallel with that guy? Because this flux would go around, oh, there'd be a flux that would go around this loop and not make it through the other coil. Now, what would I do with the other one? The other leakage? Yeah, he would basically shunt this guy so that some of the flux would go around this loop and not make it around. So if I call this would be phi L1 here. This would be, I guess, phi, what I've defined as the flux that goes through both. And this here would be phi L2. So if I said to you, what is phi 1? What's the flux going through coil 1? Well, it would be what? I'd say it's whatever the leakage flux is, plus what? Whatever the mutual flux is. So whatever flux is leaking and not making it to coil 2, plus the flux that goes through both of them. You guys with me on that? Okay. So I've got that combination of them. That's my circuit model from a magnetic perspective. How do I turn that into an electrical circuit model? I need to go from the flux linking any one coil to the flux linking all of the coils. How do I go to the flux linking all of the coils? That's lambda 1. How do I get to lambda 1 if I know the flux? There's a formula for that, isn't there? What is it? Yeah, so it's n, yeah, basically the total number of turns times phi 1. Yeah, and that's going to turn into something that looks like this here, right? I don't want to spend a whole bunch of time doing math on this whole thing. It's going to turn into this. All right. So if I look at this thing, let's just forget that I wrote everything else out here. If I look at this, this, and this, those three terms, okay? Let's look at the first term. Anytime I have an n squared over a reluctance, just in general, if I have an n squared over a reluctance, what do I have? What is that? That's an electrical circuit element, isn't it? It's an inductor. So what I'm saying is the first term here, that guy is what I call a leakage inductance. That's the inductance of the leakage path. This guy here, N1 squared over the reluctance of the core, we've already seen that. We called that the magnetizing inductance. And then this guy we called the mutual inductance. And I relate this just like I did when I didn't have leakage, I relate that to the magnetizing inductance. And I end up with this expression here. I basically have that lambda 1 equals L leak 1 times I1 plus L mag times this sum of currents here that I called I mag. Okay. So I've got that combination of stuff. So what I do, so if you look at the math, I don't want to go through the process again, but I did the same sort of mathematical manipulation process that combined those two terms. And again, I don't want to get too lost in the math because essentially I do the same thing. What I do is I added I take the circuit model that I derived. If I did a KVL around the loop here, so if I put a voltage source right here. All right, if I put a voltage source around the loop right here and I did a KVL around this loop, I would get this result right here. That's the same result. If you follow through my math carefully at home later, you'll see that this result here matches the result I would get from KVL. This is my complete circuit model. All right, what I've included is what I call leakage inductance. So this is basically the impact, and this is maybe the most important thing for you guys to worry about. The derivations, you're never going to remember that stuff, right? I don't want to focus on the derivations. If I look at this, right, what I have is for my transformer, if I put it on a core that has a really high permeability, it's got an ideal transformer in it. It has the impact of the fact that there is flux going through the core, the fact that I have to magnetize the core. And then it has the impact of the quote unquote leakage. The fact that some of the flux that's inside of the device is really not useful flux to me. It's not reaching to the ideal transformer and helping the coupling between the two coils. That's kind of what this represents. Yeah.
So if you have a L mag, I mag, why do you not have that for the secondary part?
Because it's not. So if I go through the process, that's a great question, right? If I go through the derivation that I just did, so if I did coil 2, I did this for coil 1. If I did the same thing for coil 2, what I would find is the equations I got would be consistent with that picture. And part of the reason why I say that is because if I look at this, and this is maybe what's important to me, is when I look at this L mag basically contains a current I mag. I mag represents the current in the primary plus the current in the secondary. So it actually represents both of the two coil magnetization impacts together in one device.
But why would you show up on the primary?
Well, because what I'm getting is I'm basically just combining the two effects on one side. And what I get is a circuit model that's entirely consistent with having currents going into the primary and into the secondary. The circuit model here is entirely consistent electrically with what I had in the magnetic circuit. It just so happens that because basically what I'm doing is combining the effects of I1 and I2 together into one inductor, right? I could do it the other way around, and I could actually have L mag on the other side. And it would represent the same thing, but it would be I2 plus N1 over N2 times I1. But we usually do it this way because technically power usually flows into the primary. And so we usually do it that way. Do you have a question? Colossus? Okay. You were waving at me. Look like. All right. So this is where we end up with our circuit model. And I add to this, all right, 3 additional things. All right, what 3 things that I add? Resistances. Now we've talked about this core loss here. All right, that's the hysteresis and whatever other stuff is going on inside the core. What's this guy? I called it RP and RS. What is that? Yeah, so what would it represent physically? The resistance in the wire, right? Resistance in the wires. Which one has a higher resistance? The one with more turns, right? So the higher voltage side is always going to have more resistance. Okay. All right. This is the circuit model that we use. And in fact, we usually actually simplify it quite a bit. So let's look at it this way. L leak 1 and L mag. Just think about those for a second. Which one's going to be bigger? The leakage or L mag? Which one is bigger? So this was N1 squared over the reluctance of the core. What do we hope the reluctance of the core is? We hope that it's not, well, we hope the permeability is infinite, which would make the reluctance really big, or sorry, the reluctance really small. So this would be really big, right? This guy we hope to be, on the other hand, very small. All right. Turns out we're going to simplify this guy down so we don't have to think about the magnetizing inductance. Now, Let's think about what the transfer, this is what we're gonna look at next Wednesday when we go to the lab. I wanna look at this, because I've said that the currents look weird. If I unload the transformer, now what does that mean to unload it, right?
Voltage up.
Well, it means to put the voltage on the primary, so I have a voltage there, but I don't connect any load to the secondary. So it's excited, and I'm putting a voltage on it to excite it, to magnetize it, but there's no load, so there's no current. This current is equal to 0. This is what the voltage will look like. This is what the flux or the B field looks like. I, which would be this current, would look ugly, ugly, ugly. All right, why did it look ugly like this? Why did I say it looked ugly? What was the reason for that? It was the material behavior, right? The fact that this behavior had this BH curve. We're going to look at that next week too. All right. There is a weird behavior of the material such that the current's going to look weird. All right. So let's look at an example problem in the short time we got left, right? Let's say I got this 20 kVA, 8,000 volt to 277 volt transformer, and I gave you the parameters that are shown here. Now notice I didn't give you L's. I gave you X's. So what does that mean that I gave you? What does that mean that I gave you? Not a typo. If I gave you X and not L, I gave you omega L. So again, we're talking about things in terms of 60 hertz. What that means is I gave you 2 pi 60 times, it's like if I'm talking about the mag here, I gave you that. Okay, so I can calculate that if I wanted to, but I don't want to. Okay. So I gave you those parameters, right? And those are pretty typical parameters that I've got. Okay. So let's say I wanted to figure out, let's say the transformer is unloaded.
Otherwise stated, you're always going to do some frequency 60.
That's right, unless I otherwise state it. Yeah. Yeah. And sometimes I won't state it because I want you to think through that that's what I mean, right? All right, so let's say I put a voltage here. Let's this guy said it was 8,000 to 277. So let's say I put 8,000 volts here. Right, 8,000 volts angle 0. Okay. And let's say I want to figure out what is I1 going to look like if this guy's unloaded. How would I figure that out? Given this circuit. Is there any current over here? If it's unloaded, that current's 0. So what's that say about the current here on the primary side of the train? It's also 0. So how would I figure out the current? I would say I1 is just simply V1 divided by what? Yep, RP plus JX leak 1. Right, so whatever this leakage guy is. Plus what? Nope.
Actually take the values for the inductors too.
So I did here with this guy. Yeah. But I mean, what's true about R core and L mag there? They're in parallel. So basically R core in parallel with J X mag, like that. If I do that math for these numbers, I get 260 milliamps, 2681 milliamps with an angle of, guess what you think the angle is going to be. Yeah. Well, let's take a look here. So RP is 32 ohms. X leak 1 is 45 ohms. R core is 250 kilo ohms and X mag is 30 kilo ohms. So let's think about that. If I had 30 kilo ohms in parallel with 250 kilo ohms, what's that going to be? Give me near 30. And that impedance is imaginary, is it not? Because it's an inductor. What about RP and X? If I put 30 kilo ohms in series with 70 ohms, what's about 30 kilo ohms, right? Basically what it says is the only thing that really matters here is pretty much L mag. right? So you would expect the angle to be negative 90 degrees. It works out to be pretty close to that, right? If I do the math carefully with the numbers, it's negative 83.1065 degrees. So it's pretty close to fully inductive, right? Not entirely, but pretty close. Now, in the seconds that I have left, what would happen if I put a load on this thing?
You have attitude.
Yeah, so in this case, with my load, let's say I put a rated load on it. What would a rated load be? How would I figure out rated load? Well, I said the transformer is rated for 20 kVA, right? 20 kVA is magnitude of S. What's that equal to? Magnitude of V times magnitude of I. So I'd say it's 277 times whatever I2 is, right? So what's the magnitude of I2? Well, so yeah, so S, the vector, is V times I conjugate. I'm talking magnitude, it's just the magnitude, right? Because the magnitude of I and I conjugate's the same, right? So I2, what is that? Well, if I do the math for 20 kVA, I get 72.2022 amps. Okay. If I go through this, and we'll have to do it a little bit more carefully on Monday, but if I do this and I say, let's put a load over here so that this guy is drawing essentially 72 amps with a voltage source here. What I'm going to find out is that this current here, if I do it through the turns ratio, is going to be like 25 amps. This guy is still going to be like the magnetizing current here, or the current that's going through these components. It's still going to be about 270 milliamps. This current's always going to be very, very small. The current through this branch here is always going to be really small because the values of L and R are going to be really big. And so almost all of the current, when this guy is loaded, is going to go in here, then through here, then out the other side. That's exactly what you want to have happen, because that's what the transformer is supposed to do, is it's supposed to pass power from that source to that load. That's its job, okay? I have a little bit that goes this way because I have to quote unquote magnetize the core. I have to get the field flowing around it, okay?
That's why you have the third place.
Well, I have it because the core is imperfect. And because the core is imperfect, what's happening is that there is some current flowing in here that has to magnetize it. If it were ideal, meaning the mu were infinite, I would not have to put any current into the core to magnetize it.
So that basically just make sure that the flux.
It's basically, yeah, it's the thing to remember is this represents the fact that to have that flux, there has to be a current to support it. I'm not putting the inductor there. In other words, it's not physically an inductor. It's a coil that's wrapped around a magnetic material. That is an inductance. It has an inductance that is represented by that. Like, it's not like I have a transformer and I put an inductor in parallel with it. It's to say that on that transformer, I just so happen to have an inductance that happens to be there, which represents the fact that I have to magnetize this core. I need a current that's going to create the flux. So we'll look at the rest of this example, and then we're going to talk more about this. But then Wednesday, what we're going to do is we're actually going to look at these things and see that the values are actually small and stuff like that. Okay, so I will stop there.